Hello everyone, my name is Chen. Today I'm going to give this talk on our work on Foveation for segmentation of megapixel histology images. This work has been done together with Rio, Mo-Chen, Domi, and Danny. The problem we are looking at in this work is segmenting the whole slide histology images by deep learning method, which is challenging because of the sheer size of the images with millions or even billions of pixels, which is much bigger than the typical input size of a deep learning model. Typical solutions pre-process each whole slide image by dividing the image into patches of fixed size or applying downsampling, which would incur information loss in either field of view, which means spatial coverage here, or the image resolution. Clinically, the trade-off would mean when reducing the patch size, one would lose global pattern. However, when reducing the resolution, one would lose local details. Such configuration is usually based on empirical experiments. However, the impact on segmentation performance is as yet unclear. Therefore, the first key contribution of this work is we perform empirical analysis to show that under typical memory constraints, that the trade-off between the field of view and resolution affects segmentation performance. And more importantly, its influence also varies spatially according to local patterns in different areas. For example, here, as in the ground truth, in the yellow box area, there are more big patterns, while in the red box area, there are more small patterns. With the big patch low-resolution configuration, as in the third column, we would have better performance in the yellow box area, while poorer performance in the red box area. However, with small patch high-resolution configuration, we will have better performance in the red box area, with poorer performance in the yellow box area. With such observation, we then propose Foveation module, a learnable data loader, which, for a given histology image, adaptively choose the appropriate input patch field of view resolution configuration to fit to the downstream segmentation model at each spatial location. The intuition behind is when pathologists annotate a histology image, they usually start with a low-resolution bird's-eye view of the whole image, then navigate their gaze through different locations and zoom in to the right extent to collect both local and contextual information. We evaluate our method on Gleason 2019 challenge dataset and achieved better segmentation accuracy than empirical-based fixed patch configuration baselines. We also compared against the top performance in the challenge leaderboard as well as average expert performance and achieved superior performance. In the following of this talk, I will first give a little bit more detail about the empirical analysis. Then we will move on to the Foveation module or method. And lastly, I will give you some results. The Gleason 2019 challenge dataset contains 322 training images, with average image size at 5000 by 5000 pixels. Each pixel is labeled into one of the four classes, including benign, Gleason grades 3, 4, 5, which indicating the different degree of cancers. The image is originally labeled by 6 experts. We then fuse the 6 annotations into one using pixel-level probability analysis method stable. Then each input image is paired with one single gold standard as a ground truth. For empirical analysis, we first train a set of different segmentation networks, each with a different combination of field of view and downsampling rate. Each is one of the small blue dots on this curve. We know that the maximum tensor size of the input patch is kept at 1000 by 1000 pixels and kept constant along the curve. The segmentation network with the best performance for each class is highlighted in different shaped marks. It is clear that there is no one-size-fits-all patch configuration of the training dataset. That leads to the best performance overall and for all individual classes. The figure on the right gives some visual illustration of such variation of segmentation performance over the different classes. Then let's move on to our Foveation module for adaptively patch configuration, which learns to automatically predict the spatial varying patch sampling strategy with respect to foveation and resolution trade-off. The architecture of this method is as follows. For each megapixel image X, we compute its lower resolution version XLR. We also define a patch extractor function that extracts a set of D, for example 3 here, patches, of varying field of view and resolution. But with different downsampling rate, they will have same number of pixels. And all those patches centered at one same location. The Foveation module then takes the low resolution image XLR as input and generates the probability distribution of selecting each of the 3 patch configurations at each spatial location. That is saying, the output of Foveation module at each location is a 3-dimensional probability vector over the extracted patches. We then use this patch probability to weight average the extracted patches into one single patch as the input of the segmentation network. The Foveation and segmentation networks are then jointly trained with the downstream segmentation loss. To visually examine the Foveation module, we use the patch probability to weight average patch size at all locations, and we plot this average patch size map over all training epochs. And we can see that the Foveation module is capable of learning clinically meaningful field of view resolution spatial distribution, starting from random initialization. Conceptually, the Foveation module has an effect of adjusting patch-wise resolution at each location as below. Comparing to the original resolution on the left, the Foveation module learns to predict to use low resolution, big pixel size on the rather homogeneous area at the top right. Whilst it also learns to use high resolution, small pixels as an edge area. To quantitatively check our results, we perform experiments on Gleason 2019 dataset. We first compare with a set of 7 baselines trained with patches of fixed field of view resolution trade-off. For example, the first 5 lines in the table gives 5 fixed patch size configurations, and then the 6th baseline will perform uniform random selection at each location from the 5 patch configurations. And the 7th baseline will average all the 5 patch configurations at each location. And ours outperformed all the baselines. And we have also compared with average experts' performance and also achieved superior results in the 2 most clinically important and ambitious classes. And we also compare our model against the top performed results on the leaderboard and also achieved superior performance in the 2 most clinically important classes. In this slide, we give some visual examples on the segmentation performance, where each row gives different test image, and then the second column gives a ground truth, third column gives our prediction, and then the rest 7 columns give the 7 fixed patch size configuration baselines. As you can see, our prediction nicely combines the advantage of using different fixed patch configurations. Lastly, this is another example for a qualitative check of the Foveation module, which plots the weighted average patch size distribution over all training epochs. And again here, the bright yellow means selecting small patch high resolution configuration, while dark blue means low resolution big patch configuration. It shows that the Foveation module can learn to rule out the background area with big patch low resolution configuration, while certain clinically important areas with small patch high resolution configurations. And that's the end of my talk. Thank you.